All right, so today's lesson is on rates of change. It's our application portion of limits. And one of the major applications that we're going to look at is velocity. I should say speed, right? Because we're not really doing vectors anymore. But whenever you have a certain dependent variable, like air temperature or something like that, you would also have an independent variable, like elevation. So the higher up in the atmosphere you go, that affects the air temperature. So the lower the air temperature. Right? And so the higher up you go, something is changing. Right? In this case, air temperature. With the case of speed, right, you can be having time pass by. Right? So time is our independent variable. You can't control that one. And then your position changes as time passes by. And so that rate of change we actually give a name we call speed. Okay, and since we've been analyzing so far slopes, and we've been looking at slopes of secants and slopes of tangents, we can analyze speed or velocity based on an average velocity or an average speed, which would literally be the slope of a secant. So notice there's no limits in this one. But if you wanted to know your speed at an instant in time, that's wanting to know the slope of the tangent at that point. So notice we do have limits in this equation. And it's the same equations we did last class. Right? It's just a rise over run, where your rise is your change in your y coordinates, where in terms of function would be the value of the function at some point minus the value of the function at another point. And then your change in x would just be the difference between those 2 points. Right? Same here, except our change in x goes to 0 because we're going to take the limit, right? There's no spacing there. It goes to 0. Now, in this equation, if you're used to me in physics, we usually have d in physics. But s is more of a commonly used one. Even in university, you'll start using s for distance. And you can think of it coming from two places. One, from the word space in English. It can come from that. But it could also come from the Latin word spatium, which means distance. Okay, so let's try a little investigation here. In this investigation, right, our speedometer is broken. So usually your speedometer would tell you your speed at any instant in time. That's broken. So even though we don't know how fast we're going at any instant, we do have our odometer, which will tell us how far we've gone. And we decide we're on a long trip because we're driving for like 4 hours. We start recording what our odometer reads at a time 0. So when we begin our experiment, and it says 62. All right. After 1 hour, it says 133. After 2 hours, it says 210 and 250, and so on after 4 hours. We want to determine the average velocity of the car over each interval. Okay, well, if you wanted to figure out the average velocity of the car, let's do the first interval. So between 0 and 1. So your average velocity then is just your change in your position over time. And so your position final minus initial, so we'll use 133 minus 62. All over time, which is 1 minus 0, which is just 1. Which we get to be 71 kilometers per hour. Okay. We can do that again if you wanted to go from 1 to 2, or from 2 to 3, from 3 to 4, or even if you wanted, you could figure out the entire interval from 0 to 4. You're just finding different secants, the slopes of different secants. I don't think in our lesson we need to do every one because it gets kind of repetitive. But if you did the whole one, let's try the whole one. So if we did the average velocity between 0 and 4, we'll get final 293 minus initial 62. All of your time interval, which is 4, minus 0. And we'll get 57.75 kilometers per hour. So notice these are very different. And it's because we're trying to find average. Now, obviously, if this car was moving with a constant speed, those would be the same, because there'd be a linear relationship, and it doesn't really matter what secant you solve for. It would all be along the line. But this is something more like this graph here. It's not a linear relationship, it's a curve. So we might be finding one secant for this time, for the whole time, or one for shorter times, or whichever secants you want to look for. Okay? You're all getting all different values. And that's why we call it average. So question 2 said, if the speed limit is 80 kilometers per hour, do any of results in part A suggest that you were speeding at any time? And I don't think they do. I haven't checked the other ones, but from 1 to 2, you're going 77 kilometers per hour. From 2 to 3, 40 kilometers per hour. And then from 3 to 4, 43 kilometers per hour. So no, they don't. They certainly don't suggest that we were speeding at any time. But question 3 says, explain why there may be other times that you were speeding. So is it possible you were speeding? Of course it is. Right? Remember, your secant is just your average over a time period. You could have stepped on the gas to pass someone, gone up to 100, and then slowed down to 60. I don't know why you would pass somebody and then slow down to 60. It's kind of mean. But if you did that, your average would certainly show that you were below 80, even though there was an instant where you went above 80. And just like up here, right? See this red line here? This red dotted line here shows the tangent at point P, and it's definitely a fairly steep slope. A fairly steep slope. However, if all we're doing is calculating the average, which is this green line between P and Q, it doesn't look like we're speeding, does it? Well, over an average period, no, it doesn't. That doesn't mean you weren't at some instant. All right, so part 4 says to compute your average velocity over this interval, so now from 4 to 7 hours, if the value of our function at 4 is 375 and at 7 is 609. Okay, so I'm going to do this down here so I have some room. So this is average again because it's over a time interval. It's not at one instant in time. Is going to be the function at 7 minus the function at 4 all over 7 minus 4. Which in our case is 609 minus 375 all over 7 minus 4, which is 3. Okay, and you'll get 78 kilometers per hour. So our average speed is still not over the speed limit. Now, after 3 hours of driving, you decide to continue to drive the subway. Why not? Let's just drive another 3 hours. A distance of 345 kilometers. If we take this value from part 4 as our average velocity, how long would it take us to get there? Okay, well, our equation was V average is change in position over time, so we're just going to rearrange this equation and write time is change in position over average velocity. Our change in position is 345 kilometers, because that's the additional distance we want to travel. And the time is 78. I'm sorry, not the time. The average velocity which we got from part 4, is 78 kilometers per hour. So that gives us 4.42 hours, because we like to drive. Okay, some examples. Our first example, we have a pebble dropped from a cliff, 80 meters high. After t seconds, the pebble, which is s meters above the ground, so now we're given a function, s of t, position is a function of time, between 0 and 4. So I'm assuming it's max to ground at 4. Calculate the average velocity of the pebble between 1 second and 3 seconds. Okay, so average velocity would then equal the change in position, which is our function at 3 seconds, minus our function at 1 second, over our change in time, which is, 3 minus 1. All right, so our function at 3 then, we're just going to substitute 3. So we have 80 minus 50, minus 5, not 50, minus 5, times t squared, so t is 3 squared. And then we're going to subtract. I'm going to put big brackets so I don't mess up with negatives. 80, our function at 1, minus 5 times 1 squared, all over 2. Right, and you can compute these. So 80 minus 5, if you want our function at 3, would be 35. Our function at 1 would be 75, all over 2. Which gives us minus 40 over 2, or minus 20 meters per second. Don't worry about the minus. It has meaning in physics and with vectors. But we're done with vectors. We're not going to talk about it right now. Just leave it as minus 20 meters per second. Don't worry about direction. So part B, we change color. It says calculate the average velocity of the pebble at these times. So 1 second and 1.5 seconds. This is interesting. It's like we're taking our secant and we're getting closer and closer and closer. Those points P and Q, we're getting closer. But we're not doing a limit yet. We'll get there. So our average velocity, because it's over a time interval, will be the function at 1.5. Final minus initial, the function at 1, which we already know, all over 1.5 minus 1. All right, so the function at 1.5 is 80 minus 5 times 1.5 squared minus the function at 1, which we already calculated. It's right here, 75. All over 1.5 minus 1, which is 0.5. All right, so we can figure out the function at 1.5. 1.5 squared is 2.25 times 10, and then 80 minus that would be 68.75 minus 75 all over 0.5, which is negative 12.5 meters per second. Now let's go on to example number 2. So example number 2 says we have a toy rocket is launched straight up so that its height s in meters at some time t in seconds is given by that function s of t. What's the velocity of the rocket at exactly t equals 4? Now we need the slope of this tangent. Right? It's what you've all been waiting for. Or maybe not. Maybe you do want to go back and do vectors. But let's do this. Limits. So let me write this out. To find the instantaneous velocity, we're going to need to find the limit as h approaches 0. Right? We're using our difference quotient here for the function at 4 plus a little tiny bit of h which is going to approach 0, so a very, very tiny bit of h, minus the function at 4, all over h. All right, I'm just going to move over a little bit here. So at the side, let me just do these at the side. So the function at 4 plus h, can't see the function anymore. Let me write it down up here. It was s of t is minus 5 t squared plus 30t plus 2. That was the function. And so what we're calculating is the velocity at some time t, where t is actually going to be 4. S of 4, v of 4 I should write. All right, so s at 4 plus h going to be minus 5 times t squared, so that's 4 plus h squared, plus 30 times t, which is 4 plus h, plus 2. Okay, so we're going to have to expand that. First, let's expand that square bracket. So we'll have 16 plus 8h plus h squared, plus 30 times 4 is 120, plus 30h, and then we've got that 2 at the end there. Right, so distribute the 5, or the negative 5 actually, and we'll have minus 80, minus 40h, minus 5h squared, and then we still have this plus 120, plus 30h, plus 2. So cleaning that up a bit, we'll get minus 5h squared, minus 10h, plus 42. Okay, so here we have the function at 4 plus h is minus 5, h squared, minus 10h, plus 45. And, sorry, not 45, 42. And if you find s at 4, well, that's minus 5 times 4 squared, which is 16, plus 30 times 4, plus 2, you get 42. So s at 4 is 42. So then we need to subtract the function at 4, which is 42, all over h. So 42s are gone. Now you can see where we're going with this. Factor out an h. We have minus 5h minus 10 all over h. I did something terrible. I did what I told you guys not to do. Always write that limit. The limit as h approaches 0. I got so involved with the algebra. All right, so h's cancel, and we're left with the limit as h approaches 0 of minus 5h minus 10, which now we can have h approach 0. We're just left with negative 10. So minus 10 meters per second. All right, so our last example, finance problem. Here we have the total cost in dollars of manufacturing X number of calculators if given by, so cost is a function of number of calculators, 10 times the square root of the number of calculators plus 1,000. Okay, part A says, what is the total cost of manufacturing 100 calculators? Okay, that we can do. We just solve for what that function is at 100. Okay, so we're going to do 10 times the square root, right? Substitute in 100 for x, plus 1,000. Square root of 100 is 10. 10 times 10 is 100 plus 1,000, so you get 1,100. That's part A. That's not too bad. You guys should be able to do that. Part B says, what is the rate of change in the total cost with respect to the number of calculators x being produced when x equals 100. So at this point, we want to know how is that cost changing? How much per calculator is it costing to make once we've made 100 calculators? Exactly. So to do that, we're going to need a limit. Right, so let me just rewrite our function down here because I need some space. So our function c of x is 10 times the square root of x plus 1,000. Okay, and to figure out that rate of change, we're going to need to find the limit as h approaches 0 for that function at 100, because that's what we want, right? The rate of change once we've made 100 calculators, plus a little tiny bit h, minus that cost is at 100, which we solved for in part A, all over that little tiny bit h. Okay, so the limit h approaches 0, so let's do some substitutions here. We'll substitute 100 plus h in for x. So we're going to have 10 times the square root of 100 plus h. And then we have plus 1,000. And then we have minus the cost at 100, which we solved for in part A, which is minus 1,100. And that is all over h. Well, I can sort of reduce this a little bit, right? Because 1,000 minus 1,100 is just minus 100. So let me replace this with minus 100. And then what I'm going to do is rationalize the numerator, right? I don't want that h by itself, because if I have h as 0, you can't divide by 0. So we're going to multiply by the conjugate of this. So we have 10 times the root of 100 plus h. And instead of minusing 100, we're doing the conjugate, so plus 100. And we're going to have the same thing on the denominator, so that I'm not changing anything. We're only multiplying by 1, essentially. Plus h plus 100. All right. So that's going to give us the limit as h approaches 0. So on the numerator, what we have here is that multiplied by its conjugate. So it's a difference of squares. So we're left with, well, 10 times 10 is 100. And then that square root times itself is just, well, itself without the square root, so 100 plus h. Okay. And then we have minus 100 times 100, so that's minus 10,000. All over, here we have h multiplied by all that. So 10 times the root of 100 plus h plus 100. All right. So this is going to equal the limit as h approaches 0. So if we multiply this 100 through, well, 100 times 100 is 10,000. And then we subtract 10,000. So that's going to go away as 0. And we're only going to be left with 100 times h, which is 100 h. And that's all divided by everything we have there on the denominator. We're just going to leave it as is for now. And you might be able to see where I'm going with this, because now I can cancel out that h. And if h approaches 0 now, this is going to approach 0. So we have 100 all over 10 times the root of 100, which is 10. So 10 times 10 is 100, plus 100, so 200, which equals a half, or $0.5. So it costs $0.5 to make each calculator once you've made 100 calculators.